Here are a few examples of simplifying radical expressions when you're not using a calculator. The first thing that you really need to complete this problems is you really do need to know your list of perfect squares, the first few perfect cubes, and a few powers of 2, because those values do come up over and over again when we complete these problems. So hopefully you're familiar with the perfect squares 1 through 10. It is good to know 1 through 15, so maybe 11 to 15 might be new, but make sure that you do have those committed to memory. And you also need to know your perfect cubes. Now, if you don't know your first few perfect cubes, you can always generate this list yourself by multiplying. Remember, whenever you cube something, that is taking the value and multiplying it by itself 3 times instead of 2 times. So if you wanted to compute 2 cubes, this would just be 2 times 2 times 2. 2 times 2 would be 4, and then when you times 2 again, that would be 8. So you could really create this list by hand if you really got stuck. It's also helpful to know the first 6 powers of 2. These values do come up over and over again in our problems, so if you have them memorized, then it will make these problems a lot easier for you. So we are just going to apply our radical rules like we learned in topic 6 to complete these problems without a calculator. So you'll notice in the first example, I have 3 to the 2/3 times 3 to the 4/3. In this problem, I have 2 values with the same base. So remember back to topic 6, when you have 2 values with the same base, that means you add the exponents. So I'm going to add this 2/3 and 4/3 together. So this would really be 3 to the 2/3 plus 4/3. Well, 2/3 plus 4/3, those have the same denominator, so I can just add the numerators. So this would be 3 to the 6/3, and 6 divided by 3 is 2. So this is really the same as 3 squared, which hopefully we know is 9. For my second example, I have a fraction raised to a fractional exponent. And if you remember, when I have division inside of a parentheses, I can distribute this power to both the numerator and the denominator. So this is the same, I'm going to use a different color. This is the same as 8 to the 1/3 power over 125 to the 1/3 power. And if you remember, the 1/3 power is a cube root. So this is the cube root of 8 over the cube root of 125. And if you look back at our list, I know that 2 cubed is 8 and 5 cubed is 125. So that means that the cubed root of 8 is 2 and the cubed root of 125 is 5. For my last example, I have 2 values with the same base. They both have base 32 and they're being divided. So that means that by my rules, I am going to subtract their exponents. I wanted this to be 6/5. I'm going to subtract their exponents. So this is the same as 32 to the 7/5 minus 6/5. You just take the base and subtract the exponents. Well, 7/5 minus 6/5 is 1/5. But the 1/5 power is the same as the 5th root of 32. So if you look back at our list here, you'll see that 2 to the 5th power is 32. So that means that the 5th root of 32 is 2. If you took 2 and multiplied it by itself 5 times, you would get 32. I don't think I wrote all of this all the way. I think this is supposed to be times the cube root of x to the 4th. Yeah, that's better. So since I have 2 values that are both being taken the cube root of, I can take the radicands, that's the values underneath the radical sign, and I can combine them using multiplication. So this would be the cube root of x to the 8th times x to the 4th. Now I have 2 values with the same base, so I add their exponents. So this is the cube root of x to the 12th. Now remember, the cube root is the same as the 1/3 power. And when you raise a power to a power, you multiply them. So this would be x to the 4th. For my next example, I have the cube root of 125 and x to the 6th. So since those 2 values are being multiplied, I can divide them up into their own radicals here. and then I can just compute each problem separately. So the cube root of 125 is 5. If you have a hard time with this, think of it as x to the 6 to the 1/3, because it's a cube root. And then 6 times the third is 2. So this would be 5x squared. And lastly, I have 64 over 2x to the 10th, and that's all being taken the 5th root of. So because I can divide the 64 and this 2, I should really do that first here. 64 over 2 is 32. So I can rewrite this as the 5th root of 32 over x to the 10th. And now remember, whenever you have a fraction inside of a radical, you can apply the radical to the numerator and the denominator separately. Whoops. So the 5th root of 32 is 2. And then I would have x to the 10th to the 1/5, which would be 2x squared, or 2 over x squared. And then my last example, again, both of these values are being taken the 3rd root of, so I can multiply the radicands and combine them to one radical. So this would be 2x times 4x squared, which is the cube root of 8x to the 3rd. Now, since the 8 and the x cubed are being multiplied, I can break them up. So this would be the cube root of 8 times the cube root of x to the 3rd. Well, the cube root of 8 is 2, and then the cube root of x cubed is just x, because your powers cancel here. So hopefully you find that information helpful when you're trying to work through the non-calculator section of your test review.